Welcome, everybody. Thank you for joining us. My name is Temba Nume. Today, our focus is grade 10 physical sciences, sound, waves, and light. Our focus today will be primarily on transverse pulses. I'm excited. I hope you enjoy our session together. Thank you very much. Right, as I've said, our focus is on transverse pulses. Now, just to get a general overview of what exactly are we on about this afternoon. We're looking at wave, sound, and light, which is the knowledge area. That's the physics part, grade 10. It is divided into a number of subtopics. The first one being transverse pulses, which is our key focus for the day, right? Okay, transverse pulses. Then from transverse pulses, we are going to look at transverse waves, right? Then from transverse wave, we'll move on to electromagnetic radiation, which has a lot to do with light, as the topic suggests. Then from there, we will also have a focus on longitudinal waves, still under waves. And then the last segment will be based on sound. I'm very much excited to go through these concepts, right? Now, having said that, okay. There we go. Okay, then we shall look at sound as our last segment. Right. Now, just to get us started, we shall quite a bit have a discussion based on the key terms that are going to be used quite often in the concepts that we shall deal with in this section. Surely, some of the meanings they carry a different meanings from the everyday language to the science. There could be quite a number of misconceptions as a result of that. Take, for example, the word medium. Medium, if you think of a stove, maybe in the kitchen, you'd understand that if you put it on medium, it's not hot, no cool, just in the middle. But in this case, it has a different context altogether. Pulse is another term that is often used in everyday life. Take, for example, if you take the pulse, it has to do with the heartbeat. But here, our focus is on waves and pulses. Then transverse, crest, trough. When you think of a trough, if in farming, the container which we use to feed our pigs, for example, we call it a trough. However, it carries a different meaning altogether in this case. We talk about amplitude and pulse length. What we're going to do, I'm very much excited. I think we already have some ideas about the terms. However, I'll just give you a couple of minutes, let's say 2 minutes, just to kind of figure out exactly what each one of those means as far as pulses are concerned. Okay, off we go. 2 minutes for that. Oh, thank you very much. Let's hope each and every one of us has tried to figure out the meaning of each of those very key terms, I must say, in this section. All right. Now, let's look at each one of them in turn. Right. Okay. Right. As far as the medium, let's maybe, as a starting point, consider a situation which normally happens every day. When a rope or a hose pipe gets stuck somewhere, we tend to give it a flick, and that flick, it travels on the rope or on the pipe itself. So we would very much want to think of the rope or the pipe as the kind of material that allows the disturbance or that pulse up and down movement to be transmitted through it. So the key words as far as a medium, we can think of a medium as a material. We can think of it as a material, right, which allows a pulse or to be transmitted through it, right. Now, mediums, they vary from one form to another. Some of the disturbance can be transmitted through the air, some could be transmitted in water, depending on the scenario under concern, right. So it's a material that allows a pulse or a disturbance. I'll use the word pulse in disturbance, oscillation interchangeably to refer to one and the same thing. That allows a pulse to pass or to be transmitted through. Right. Okay. So generally, you'd understand that the word medium has a totally different meaning from what we know compared to that of a scientific concept. Now, let's talk about the pulse. Remember, our key focus today is on transverse pulse. Remember, the moment you give the rope a nudge or that flick up and down, it generates a movement which is transmitted through the rope. So let's think of this. I'll use the sketch on our screen now as an example. Right. This up and down movement consists or gives us what we refer to as a pulse. So a pulse is a disturbance. Now, if you look at the other parts of the rope, the other parts of the rope are at a point where there is no disturbance, or pretty much refer to it as a zero disturbance. So we call this the rest position. The rest position. Rest in the sense that there is no disturbance or oscillation that is moving through that part of the medium. Remember, now the green, which represents our rope, is the medium in this case. So the rest position, it's sometimes we refer to it as the equilibrium position. Okay, right. Now, as far as the pulse is concerned, which is our key idea for today's lesson, the pulse will be a single disturbance. Remember, the flick is only done once. However, it travels through the medium, the material. So as a result, a pulse would maybe think of it as a single disturbance that moves through a medium. Okay, that moves through a medium. Right. So the medium in this case, remember, it is the rope in the context that we spoke about. Right. It goes further. On the same note, I want us to think of the fact that also the pulse starts at that point. Let's call maybe that point A, and then let's call that highest position B. That's the upward disturbance in terms of the pulse motion. And then let's call that C, let's call that D, let's call that E. I want us to realize the fact that A to E consists of a single pulse. However, in real life, when we talk about a pulse, usually when we do one flick, it only consists half of a pulse, because a full pulse, it consists of up and down, then go down and come back to rest position. So that's a complete single disturbance, which is our pulse. So, and then if you look at the pulse, this is the point B is a point of highest disturbance from the rest position. If I could use the dotted line to indicate where the rest position would be if there was a zero disturbance. So point B is the crest. So the crest of the mountain, say for example, is the highest point of disturbance from rest position. In this case, it's in the upward direction. If we want, we may look at it that way. So point B is the crest, very key component of a pulse. And then if you look at point D, it's the same disturbance from that rest position, but in an opposite direction or downwards. So the lowest position or point of disturbance, we call it the trough. The trough. So the crest and the trough are the same distance from the rest position to the lowest points of disturbance, as well as from rest position to the highest point of disturbance. In this case, we have our crest as well as the trough. Very important. Now, if you think of it, this distance, sometimes if the flick is done in such a way that it has a greater disturbance, it affects what we call our amplitude. Right. So in this case, our amplitude is this distance from rest position to crest, or from rest position to trough. Very key to remember that. In other words, from the rest position to point B, it will be the same distance as the distance from rest position to our trough. So the amplitude is the maximum displacement or disturbance maximum disturbance. Right, maximum disturbance. Remember, the disturbance is the one that creates a pulse. Maximum disturbance from rest position, to the crest or to the trough. So the amplitude obviously will be measured in meters, because we're talking about distance in one dimension. So our amplitude in this case is from rest position to B, which is the same distance as well from the rest position to D. Remember, D is the trough and B is our crest. Right. Okay, guys, I think our discussion is in terms of the key concepts or the components of a pulse that is created in a medium does make sense to us. The last key concept or key component of a pulse that I would want us to discuss is the pulse length. Now, back to our sketch. Point A is the beginning of our pulse. It ends at E. Remember, this is a single complete disturbance that has occurred in a medium due to the flick. Remember, so the medium being the rope. Now, if you consider distance A, E, it is what we'll refer to as the pulse length. Now, come to think of it, if we do a single up and down flick motion, it only creates or generates a half of the pulse. So under normal circumstances, we would see AC in real life. However, if we do a complete, which consists of up and down, then going down to the trough, back to rest position, it will generate or propagate a pulse of a single disturbance that has happened in that medium. So AE is the pulse length, which has to do with the distance or length of a single pulse. Okay. So pulse length is the distance or length of a single pulse. Right. Right. Obviously, the units, if you want to think of it, they are in meters, because it's a simple distance in a straight line from A to E. Right. I think we've done quite a lot for now. Let's take time off and maybe drink some water, refresh, and we join again when we go to the next segment of our very interesting section. Thank you very much. Hello and welcome back, guys. Let's look at the next concept, which has to do with transverse pulses. I think our previous discussion, we looked at the key concepts or components that make up a single pulse that's propagated or produced in a medium. Right. If you come to think of it, the transverse pulse has to do with two very key aspects. Number one, it has to do with the disturbance itself, right? The disturbance, very key, as well as you'd have realized, when you flick the rope, there is the motion of the disturbance, right? Now, think of it, in which direction does the pulse move? along the medium in our example that we did with the rope in our earlier discussion, and also think of the particles of the rope in terms of the disturbance. In which direction of the medium do they move? So in this case, we're talking about the disturbance and also the movement of the pulse itself. Movement of pulse. All right. Okay. So now, the two big questions that we need to maybe unpack now is the direction of the pulse movement. Remember, the pulse itself, that's half a pulse anyway, remember very well. So that's half pulse the length, the direction in which it moves, okay, as well as the direction of the particles. Right. I want us to go to a PhET simulation, which will maybe create a better understanding of exactly what happens as far as the disturbance and the pulse in terms of its motion. Right. Okay, now what we have right in front of us is a PhET simulation. It's a resource that can be used. We can play around it to try and figure out quite a lot of concepts as far as particles of a pulse are concerned in terms of movement and of the particles, as well as the direction of motion of the pulse itself. Right. So think of the beads in this case as our particles, right? And the disturbance which is going to be transmitted through the medium, right? If I'm going to click on that, you see, there is a disturbance that is generated. I want us to realize the movement of the particles, or the beads in this case. They are moving up and down, yet the pulse itself, half the pulse rather to be precise, is moving horizontally. Right. If you can watch that, that's the upward movement. Because the end is fixed in that case, it allows the pulse to go back and forth. So think of this as the rope, and you're just given it half the flick. As a result, or consequently, it has generated half a pulse, which is transmitted through the medium. Very key concept. Right, I'll stop it there for a while. If you can realize, the particles or the beads, they move up and down. We can think of it in one plane as a vertical, right? And then the motion of the pulse, which is half the pulse in this case, is moving horizontal. So from our maths, we would understand very well that if the particles are moving up and down, and the pulse is moving horizontal, the two make an angle of 90 degrees. If I can play it further, just for us to further investigate that, I think it makes sense. Right. Now, back to our key questions. Right. In which direction does the pulse move? The pulse moves horizontally, right? It can either left or right. Okay, horizontally. Right, in a straight line, it moves horizontally. And then in which direction do the pulses of the medium move, or the particles rather? Remember, our particles in this case are the beads. They were moving up and down. So horizontally versus up and down, okay? We can think of it as vertically, right? Okay, now as they move, I think what is also important is that this is the up and down movement of the particles, as well this is the horizontal movement of the pulse. This is the movement of the pulse, right? Remember that pulse was half a pulse, it's fine. However, the point that we want to drive home is that if the particles move vertically, which is up and down, and the pulse move horizontally, they make an angle of 90 degrees. So the key term that comes to mind is that these two are moving perpendicular to each other, right? So as they move perpendicular to each other, this is a key aspect or a key characteristic of what we refer to as a transverse pulse. So in a transverse pulse, in a nutshell, what can we say? So a transverse pulse, by definition, pulse, okay? Remember, the pulse is that single disturbance that was transmitted through the medium. Our key focus in this case is the transverse nature of the pulse. Now, if you look at the pulse, the particles were moving perpendicular to the direction of the pulse movement. In this case, a transverse pulse is the kind of a disturbance in which a disturbance so it's a disturbance that occurs in a medium, in which particles move perpendicular to the direction of motion of the pulse. Okay, in other words, the disturbance, which is up and down, is perpendicular to the direction of motion of the pulse. Okay, so the key word in this case geometrically is perpendicular. Remember, perpendicular suggests that they are moving at an angle of 90 degrees relative to each other. Of the pulse. Okay, so there are two components: the particles moving up and down, and the pulse moving horizontally. Right, now moving along. With that understanding, remember, as we talk about pulses, we need to bear in mind that these pulses may be generated. You can have one or two from both ends. Let's say we have the rope. One learner is holding the rope on one end, and the other learner is holding the rope on the other end. So what is happening? Primarily, we're going to have two pulses. Right, in this case. Now, if you check, the concept of superposition has to do with how pulses interact in space if they meet. Now, let's say this pulse is moving in that direction. Let me just go to the pen. This one is moving in that direction. This one is moving in that direction. Now, you'd realize the key components, again, that's our crest. Let's say this crest is X, and then that crest is Y. Now, they are moving towards each other. Now, as far as superposition is concerned, it has to do with exactly what happens when two pulses meet in the same space at the same time. Right. Now, if we can move those pulses to each other and see what exactly happens. So this one comes over, and what's going to happen is they'll be at the same time in the same space. Now, what's going to happen? They will be on top of each other like that. However, what will be very important is that the resultant disturbance, each one of them has their own amplitude. In this case, let's say the first one had an amplitude, let's say, of A, okay? If I may take that back, okay? This one had an amplitude of A, right? Remember, amplitude, again, from our prior discussion, amplitude has to do with the distance from rest position, okay, to the maximum point of disturbance, okay? Right, now, that's amplitude A, okay, generally there, and then we have the other pulse, which is approaching from the other end, right? It has also, let's say, its amplitude is B, right? So these two are going to meet at some point because they are moving towards each other in opposite direction. Now, okay, let's say, for argument's sake, they now meet each other. I'm going to move that one towards the other one. So when they meet, superposition takes place. However, something is going to happen as far as the amplitude or the resulting disturbance from rest position is concerned. So instead of having the very same magnitude or size of disturbance, would have an even greater disturbance. If I could use green there, okay, right, okay. So the resulting disturbance in this case will be much greater compared to the individual disturbance. When that happens, we then say superposition has taken place. And hence, we can use the word interference. You know, when you interfere with somebody, you kind of disturb. In this case, one of these two, they are met in the same space at the same time. So the resulting disturbance between which occurs as a result of the two pulses is concerned, it's let's say A plus B in this case. Now we had a crest meeting a crest. Once they've met with each other, they would obviously pass each other. The other one will continue in its original direction of motion, yet, okay. The other one will also continue in the other direction, right? So as a result, we say superposition have taken place. In this case, these two pulses have met, a crest has met another crest, okay? We call that constructive interference. We call it constructive interference. Now, in other words, we're thinking of these 2 points as in phase, or in other words, they are the same, rather, they are from the rest position to the highest point of disturbance. When they meet, there's constructive interference. Now, another possibility is that we may have the two pulses meeting in different directions or in opposite direction. Take, for example, in this case, we've got a crest meeting a trough. Remember, in our earlier discussion, we also described what it means when we refer to a part of a pulse as a crest or as a trough. So when they meet, in this case, we would have one approaching the other as they move towards each other. Then we'll have this kind of a situation. Now they will superpose on each other, if I can put that somewhere there. Okay, right. So the resulting disturbance, remember, is the sum of the two disturbances. In this case, we are talking, when we talk about the disturbance or the size of the disturbance, we're talking about the amplitude. So the resulting disturbance, when they meet at that time, it will exactly, they will cancel out each other in this case, provided that they are of equal amplitudes in opposite direction. But the moment that happens, then superposition has taken place. But what do we call this kind of superposition? We call it destructive interference. We call it destructive interference or superposition. So once they meet, they pass each other at that stage, okay? And when they pass each other, they continue in their original direction of motion at their same speeds. Right. Now, that's as far as constructive and destructive interference are concerned. Right. So two key things here. We've got 2 points meeting in phase, a crest meeting a crest, or it could be a trough meeting a trough. We would have then constructive interference. On the contrary, when we have a crest and a trough meeting, then we have destructive interference. That was, I think, the key idea that we need to take home in terms of explaining what superposition is. However, also, what is key is that the resulting disturbance when the two pulses meet is the sum of the two. Remember the A plus B? Okay, the A plus B. So those are the key ideas as far as superposition is concerned. For now, we'll take a short break, and maybe when we come back, we shall look at the brief activities to check our understanding on this very interesting concept. Thank you. Hello and welcome back, guys. Hope everyone is well refreshed now, and we're ready to do the remainder of our segments. I want us now to look at the questions that are based on the concepts that we have discussed. We've got 2 questions, one long questions, and the last one, which is brief and direct. Now, let's look at the questions on the screen now. Now, the first one says, a pulse. It's very important to go through the question and understand every aspect of it. Right. It says a pulse. We already know what a pulse is. Okay, a single disturbance, blah blah blah. That moves through a medium. It has an amplitude of 10 centimeters. Is moving to the right. That's the direction of the first pulse, and another pulse of amplitude 15 centimeters in the same rope is moving to the left. Now, these two, if they're going to meet each other, they're moving towards each other, in other words, in opposite directions. Now, we have a clear understanding that they will meet at some point. Right. Now, if I can draw your attention to the first few questions that I'll give you 3 minutes to go through. The first one says, state the principle of superposition. The emphasis is on the principle, right? So you'll obviously write it in words. Right. Then the second question says, draw separate diagrams to show the pulses as they approach each other. Remember, for the purpose of superposition, we're going to use half the pulses to demonstrate what exactly happens as far as interference is concerned. Now, the first diagram will show the two pulses on the same medium approaching each other, right? And then the next question, 1.2.3, would show when they meet each other. Now, this is what is going to happen, guys. I'm going to give you, say, 3 minutes to do the 3 questions, to state, draw as they approach and meet. And after that, we'll do the remainder of the question and do feedback as a collective. So let's go on to it, guys. All the best. Welcome back, guys. Surely you've tried and attempted the questions, the 3 questions. Now, this is what is going to happen. We'll look at the 3 questions in the same question, sub-questions, the 3 of them. I'll give you a further 3 minutes. Right. Remember, the other one is amplitude 15 centimeters, meeting an amplitude of what? 10 centimeters. Now, if you can go to the last question now on the screen, you'll realize that we have got question 1.2.3, which says you need to draw, remember, this is from question 1.2. You need to draw the pulses. Now, our focus when they have past each other. In other words, when interference has taken place. And then the last question, it says you must state what type of interference is illustrated above. So it's when they approach, meet, and when they've passed each other. Then this would, the last question, we have to state the type of interference. Okay, I'll give you 3 minutes to do that. All the best, guys. Let's get on to it. Okay, welcome back, guys. Thank you very much. I hope you have attempted the problem. Let's quickly have a look at, do the feedback and check how we did in each one of those questions. Right, okay. Yeah, the first one, it says, state the principle of superposition. Remember, the principle of superposition explains what happens when two pulses meet in the same space or when there is interference. So it says that when two pulses meet, meet in the same space, remember, the resulting disturbance, okay? The resulting disturbance is the algebraic sum, okay? So if it's the two crests meeting, we will add. If it's the two troughs meeting, we'll add. And then if they are in opposite direction, we add, we subtract, obviously, because they're in opposite direction. The resulting disturbance is the algebraic sum of the two, okay? So algebraic, remember our A plus B, okay? In our earlier discussion. Algebraic sum, in other words, is the total of the two, right? Okay. Having said that, so this is the principle itself of the two pulses. Okay, if I can indicate that as well. Right. Now, if we consider the two pulses approaching each other, right, there's the first one. Remember, the 15 centimeter pulse is bigger than the 10 centimeter, right? So if when they approach each other, let's say, for argument's sake, this is our 10 centimeter pulse, and then this is our 15, okay? These diagrams are not necessarily drawn to scale, but we know that is 15, okay? Then that is the 10 centimeter, okay? Now, that's from the rest position. That one is moving in that direction. That one is moving in that direction. So that one is 10 centimeter, okay? Right. Okay, right. So this is primarily what happens when they approach each other. Remember, according to the principle itself, when they meet each other, the resulting disturbance is the sum of the two. Now, instead of having 15 and 10 separate at the same space, when they meet, would have an even bigger disturbance, which will be the algebraic sum. In this case, it's our 15 plus 10, if we can indicate that, which gives us what? 25 centimeters. So when they meet, at the point that they meet, the resulting disturbance will be exactly 25 centimeters, to be precise. Okay, be careful with the units because they are given in centimeters. We need to show. So by the time that they meet, this is primarily or basically what is going to happen. Okay, when they've passed each other, remember, they are going to have to continue moving in their opposite direction. That's our 15, that's our 10. So the 10 is continuing, moving to the right. The 15 will continue moving to the left, okay? Even if we don't show that, we show that they have passed each other. So that's 10 centimeters, okay? That's 15 centimeters. So this is what has happened. Now, I want us to realize the fact that if you can go back to when they were approaching each other, we indicated that in this case, we have got a crest meeting another crest, a resulting greater disturbance occurred. So in terms of classification, there are two types of interferences when superposition takes place. Because these two, we have two crests meeting, then we have got what we call constructive interference, right? It's called constructive interference, okay? So these two have met in phase. These are some of the terms that we are going to use quite a lot in our follow-up session. When we say in phase, it means it's a crest and a crest, or alternatively a trough and a trough. So that was it, Lenas. Now I want us to quickly look at the last question. I want us to look at the last question, which is based on the speed of a pulse. Remember, a pulse is generated from in a medium, and it moves a particular distance, right, in a medium, right? Okay. If I can draw your attention to the screen, you'd realize that it says it takes 0.5 seconds. 0.5 seconds is the time to produce a pulse which moves a distance of 500 millimeters. Now calculate the speed, how fast the pulse is moving. Now our units of speed that we shall use are meters per second. I'll give you a minute to do that. Remember, speed, meters per second. We're given the time. We're also given the distance. Now the units are meters, which would be the distance, as well as time in seconds per second. Let's get on to that. 1 minute for that, Lenas. Okay, welcome back, learners. Let's look at the question very quickly and do the feedback so that we can do an overview, summary of everything. Now, remember, we're given the time. And if you look at the units, it's meters. The units are in meters, meters per second. In other words, what we are saying, remember from your maths in grade 9, when you talk of speed, in this case, when we talk of speed, we shall use symbol V, right? And speed is measured in meters per second, okay? With that in mind, then we say V is equals to distance moved by pulse divided by the time that it took the pulse to move that particular distance. So our distance in this case is in millimeters, and we know that in a meter, there are 1,000 millimeters. Because it's 500, then we know that the distance, if we divide that by 1,000, we'll get a half a meter. Half a meter, it's 0.5 divided by 0.5. Okay, these are meters and these are seconds. Remember, our answer must be in meters per second. So you divide that, you get 1 meter per second. Now, that is the speed of the pulse. In other words, in every second, the pulse moves a distance of 1 meter. Right. Okay, guys, now after all has been said and done, what is it that we need to take home at this point in time? We looked at the transverse pulses, right? The transverse pulse, okay? Remember, the key things about the transverse pulse is that the disturbance is up and down, say, for example, and the direction of motion of the pulse is what? Horizontal. In this case, they are perpendicular to each other. We also looked at superposition in terms of the principle, which explains what happens when interference takes place, okay? So it's superposition explaining interference, right? Two pulses, when they meet, interference, when they meet in the same space at the same time. And also we looked at wave speed, okay, how fast a wave, or a pulse speed rather, because the pulse, okay, the pulse speed, okay. Those are the key things that we discussed today and the key components of a transverse pulse. Now, hope you had a very interesting session today. I did enjoy it. Let's hope we meet each other again in our next session. For now, thanks and goodbye.